In this episode, we are going to take a look on how to draw this triangle using the programmable pipeline, which is also called the modern OpenGL. So for this, we are going to actually need to modify the code and to involve shaders and vertex buffer objects, or also called VBOs. So here, first we are going to create the vertex and the fragment source. Then we are going to compile it to a shader program, then tell OpenGL to use this program, which will be run then on the GPU or the graphical processing unit. And then we are going to create a vertex buffer object and send the vertex data to this vertex buffer object, or VBO. So let's get started. So I'm just going to delete the old deprecated function calls. So these four: enable client state and vertex pointer. So I'm just going to delete these. And here, after the imports, I'm just going to paste the vertex shader and the fragment shader, although I'm just going to call them vertex src for vertex source, because these are just the sources, and fragment src for fragment source. So let's take a short look how this vertex and the fragment shader looks like. So first we are specifying, as you can see, first this is a multi-line Python string, and the first line of this vertex source specifies that we are going to use GLSL version 3.3 and the core profile. The second line is just an attribute of input vector 3 called a_position, and the A stands for attribute. Then we have a void main method or function, and here we are setting the GL position, which is inbuilt type, vector 4 type in GLSL, to equal to vector 4 of attribute position. And because attribute position is a vector 3 and we are using here vector 4, we need to specify the fourth as which is a W, to be actually just 1. And in the fragment source, we are also specifying that we are going to use the version 3.0 core profile, and we are creating an output vector type vector 4 called outColor or out_color, and in the void main we are setting this outColor to be equal to vector 4 and 1, 0, 0, 1, which will be the red, green, blue, and the alpha values for the fragment source. And now let's do the shader compilation, and for this we are going to import from OpenGL.gl, GL with capital, that shaders module. We are going to import the compile program, and also the compile shader functions. So these two functions. And now let's compile these. So here, after we created the context, and let's say after the colors, I'm going to create a shader variable or shader object, and I'm going to use the compile program, and inside as a first parameter I'm going to call the compile shader function with the vertex source, vertex src, and tell it to compile it to a gl_vertex_shader, vertex shader. And as a second parameter to this compile program will be also the compile shader, and we are going to give it the fragment source and tell it that this will be a GL fragment_shader. So if you just open up, I'm just going to close these tester files. If you open up this compile shader, you can see that it calls the compile shader from the OpenGL, and it compiles down to a shader program, and the compile program actually attaches the shaders to the program and also links these two programs, or I mean links this program, and it also just validates and checks if it is linked. Sometimes it is also useful to actually open up the source code and check what it does under the hood. So this is how easily you can compile a shader program inside by OpenGL. The next thing, I'm actually just going to tell OpenGL to use this program. So GL use program and the shader. So now we have a valid vertex and a fragment shader, and I mean a valid shader program. So if I run, we still need to actually have the vertex buffer to actually see the triangle. So this will be the next step to actually create the buffers. So let's say here, or after the shader compilation, I'm going to create a VBO and set it equal to GL gen buffers, and we are going to generate one buffer. And I actually recommend you to go online to this site, which is called docs.gl, if you want to know a little bit more. Here's the GL gen buffers. If you are using it with C or C++, you specify its size, or specifies the number of buffer objects names to be generated, and second argument specifies an array in which the generated buffer object names are stored. So in Python you actually just give it one parameter, which is this n. And now let's tell OpenGL that we are going to bind this buffer, bind buffer, and we are going to bind the GL array buffer, GL underscore array buffer, and using the VBO. So let me take a look at the GL bind buffer. Bind a named buffer object. The target as the first argument to this function specifies the target to which the buffer object is bound. The symbolic constant must be GL array buffer, that's what we are using, and all of these others. And the second argument is the buffer itself, specifies the name of the buffer object, so this VBO. And now let's send to this array buffer, or to this VBO, the actual data using the GL and buffer data. And the buffer data also needs as its first argument the array buffer. The second argument is the number of bytes. So we have, in these vertices, we have 3 times 3, which is 9 elements, and each of this element is a 4-byte float, or a 32-bit float. So to actually get this data, we can use just the length of the vertices, vertices, and times 4, not divided, but times 4. And the third parameter is the actual pointer to the vertices, and the last parameter, so here it is buffer data. So first was the target, which was the array buffer, the second was the size, and data specifies a pointer to data that will be copied into the data store for initialization, or null if no data is to be copied. And the usage, we are going to use the GL static draw. So let's set it to GL underscore static underscore draw. Okay. The size. You can actually calculate it like this. So the length of vertices, which returns the length, how many elements are in this vertices list or array, and each element has 4 bytes, so times 4. Or there is an easier solution, just to replace it with vertices, that n bytes, which will return the same value. So in this case we have 9 vertices, and so 3 times 3, and each vertex has 4 bytes. Its size is 4 bytes, so 9 times 4 is 36. So these vertices that n bytes will return 36. And the next thing we need to do to actually set this attribute location, this input vector 3 a underscore position. So here I'm just going to get first the position, and this will be equal to gl.getPosition. get attrib location. Get attrib location. And let's tell it that get the attribute location from the shader program, and the attribute name is underscore position. So this has to be the same, a position, as it specified here in the vertex shader, a position, a underscore position. So this will store the attribute location, a position, in this variable, and now we can enable this vertex attribute array using the GL enable vertex attribute array, and the position, and the last thing to actually do is set the vertex attribute pointer using the gl.vertex attrib and pointer. So the vertex attrib pointer, as its first argument, here it is, vertex attrib pointer. The first argument is the index, which specifies the index of the generic vertex attribute to be modified, and this is actually the position. The second argument to this function is the size, specifies the number of components per generic vertex attribute, must be 1, 2, 3, or 4. So we have 3, because we have 3 vertices. And the third argument is the type, specifies the data type of each component in the array, which is GL float. So GL underscore float. And let's see this next, which is it should be normalized or not, and we are going to set it to GL false. So GL underscore false. And the last two arguments is the stride, specifies the byte offset between consecutive generic vertex attribute. If stride is 0, the generic vertex attributes are understood to be tightly plugged in the array. The initial value is 0, and we are going to use also just 0 here. 0, so it's tightly plugged. And the last argument is the pointer, specifies an offset of the first component of the first generic vertex attribute in the array. And for this we are going to specify the offset as c types that c void pointers, so c underscore void underscore pointer, and let's set it to 0. And now we should have the same triangle, but now using the modern OpenGL. So we created two shader sources, the vertex shader and the fragment shader, and when you are using the programmable pipeline, these two shaders has to be specified, the vertex and the fragment shader. You can also have a geometry shader and a tessellation shader, but those are optional. But the vertex shader and the fragment shader must be actually specified. So then we just created a shader program. We created a vertex buffer object. We bind this buffer and we send the data to this buffer. Then we are getting the attribute location called a position from the vertex shader. We enabling the vertex attribute array, and we setting the attribute pointer. And then we are telling OpenGL to use the program shader. And now let me run it. And we have a triangle, and it is the whole triangle is colored red. So here in the fragment source, as an out color, we set it to a vector 4 of these values. So red, green, blue, and alpha. As you can see, full red, 0 green, 0 blue, and full alpha. So here in the vertex and also in the fragment shader, I'm specifying the version 3.3.0 core. And this core is the default, so you can just leave this out if you want, because if you go to this page, so kronos.org OpenGL wiki, you will see here, the version number can be followed by the profile name, and this can be core or compatibility. If a profile name is not specified, the default is core. So in this case, we didn't specify it, so the default will be core. And if you set it to compatibility mode, it means that it will be compatible with older versions of GLSL. In some cases, it can be useful. And one more thing I want to actually show you is this online book called learnopengl.com, and the guy who wrote this book uses C++, and he also uses the GLFW for windowing, and I think this is the best book on the OpenGL topic, and I'm going to add the link to this book in the video description. And I'm also going to add the link to this docs.gl, so you can actually search for all of these GL functions and just take a look which function what does. And to actually finish this triangle so that it will have the same colors as before, so red, green and blue, in the vertex shader we are going to specify another vector 3, and this will be a_color, so attribute color. And I'm also going to create an output vector 3, and this will be v_color, and v stands for varying. So, and the varying in GLSL means that it will be passed from the vertex shader to the fragment shader. So here, after the GL position, I'm going to set the v_color equal to the a_color. So in this way, the v color will be set to a color, so the attribute color or the input color. And here in the fragment source, I'm going to create an input vector 3, which will have the same name as this v color. So I'm just going to copy this and paste it here. And now in the out color, I'm going to set it to v_color. So the v_color is a vector 3, and this accepts a vector 4, so this is vector 3 and this is the fourth argument, so which will be the alpha value. And to actually set this a color or this attribute color, I'm just going to copy this, and here, or I'm just going to copy these 3 lines and paste it here. I'm going to change this to color. Here it should be a_color or attribute color. Here enable vertex attribute array color, GL vertex attribute pointer for the color. So we have still 3 values of type GL float, GL false for normalization, and the stride GL vertex attribute. So the stride is 0, and the pointer will be C-type the C_void pointer and 36. And I'm going to here this color, actually I'm going to delete this and just make one big buffer. I'm going to delete also this line. So here now we have just one big buffer, and this buffer has the first values are the vertices, so the first vertex, the second vertex, the third vertex, then the first color, the second color, and the third color. So we just concatenated the 2 buffers, so we now have just one buffer. And we need to tell OpenGL that these values are the vertices and these values are the colors. And here, when I'm specifying that the colors starts from the 36th byte, so which means here we have 9 values, and 9 times 4 is 36. So from the 36th offset, or from the byte offset of 36, they're starting the colors. Hopefully it was understandable. So now when I run this, we have our colored triangle using the programmable pipeline or the modern OpenGL. So once again, each of these values have 4 bytes. So when you specify here, you specify that the position starts at the 0 bytes. So here, this is the 0 bytes, and it is tightly plugged. So we have one position, and after one position we have the second position, and after the second position we have the third position. And here it says that the colors starts at the 36th byte in this array, so which is this one. and we have the first color, and it's also tightly pugged. Then we have the second color, and lastly we have the third color. And yes, so you can have multiple ways to actually define these buffers. You can just say that, okay, I'm just going to have one vertex, then I'm just going to copy this, then its color, then the second vertex and its color, then the third vertex and its color. So I'm going to delete these spaces here, and I'm also going to move this here and add here some commas. But when you rearrange your buffers, now it looks like this, so it just skewed this triangle. You also need to tell OpenGL here, when you specify the vertex attribute pointers, how to read this buffer. So in this case, it will be, we have 3 vertices and 3 times 4 bytes each, and then starts a color. So it means that that here as a stride we need to specify 24, and here also by these 24, which means we have in each row we have 6 values times 4 bytes, which is 24. So the vertex here starts at 0, and the next vertex starts at 24 bytes, and the next vertex another 24 bytes. And for the colors, now the color starts not at the 36th byte, but they are starting here, which means 3 times 4 bytes, so they are starting at the 12th byte. So if you rearrange your buffers like this, you need to also make sure you correctly calculated the bytes offset for also for the stride and also for the pointer. And now if I run it, I should have the same triangle.